Please turn off your device camera. Participants are muted by default to enable the speakers to present without interruption. Participants can ask questions by visiting slido.com using the code BioInfoLecture or click the link in the chat box. To ask your questions, state your name, affiliation, and the question you want to ask. You can also upvote questions already posted by other participants. To get your certificate of attendance from this webinar, fill out the evaluation form. The link will be posted in the chat box at the end of the webinar. Please turn off your device camera. Participants are muted by default to enable the speakers to present without interruption. Participants can ask questions by visiting slido.com using the code BioInfoLecture or click the link in the chat box. To ask your questions, state your name, affiliation, and the question you want to ask. You can also upvote questions already posted by other participants. To get your certificate of attendance from this webinar, fill out the evaluation form. The link will be posted in the chat box at the end of the webinar.
Tayo po ay magsitayo. Bilang pagpupugay, ilagay ang kanang kamay sa ating dibdib at awitin ang pambansang awit ng Pilipinas.
Project staff of the Philippine Genome Center, Mindanao. Ladies and gentlemen, your host, Dr. Joel Hassan Tolentino.
Good afternoon, everyone. Thank you for taking time to join this webinar. And on behalf of the Philippine Genome Center, Mindanao, welcome to the first Bioinformatics Lecture Series. I am Joel Tolentino, and I will be your host for today. This lecture series is a collaboration between the Research and Development Division and the Bioinformatics Division of PGC Mindanao. This event will bring you exciting bioinformatics topics as applied to diverse fields. Last October 1, we had our first lecture series where Mr. John Divina of PGC Mindanao talked about the toolset of agricultural genomics. Today, we will be featuring one leading UK academic from the University of Birmingham, who will be sharing with us UK efforts in contributing to studies related to COVID-19. To start off with our second lecture, let me introduce the moderator for this session. Our moderator is a former faculty member of the UP Diliman Department of Computer Science and is now a full-time personnel of the core facility for bioinformatics under the UP Philippine Genome Center, where he currently serves as its director. He is also the current director of PGC's Computational Genomics and Systems Biology Research Program. Everyone, please help me welcome Dr. John Michael Yap. Dr. Yap, good afternoon.
All right. Good afternoon, Dr. Tolentino. And thank you very much for the kind introduction. I'm experiencing some sort of technical difficulty. I can't seem to start my video, but nonetheless, okay, I'm not I guess the one that is more important here is the distinguished guest and speaker for this episode of the PGC Mindanao Bioinformatics Lecture Series, who I am about to introduce. Okay, so our speaker is the chair of Bioinformatics and director of the Center for Computational Biology, as well as a member of the Institute of Cancer and Genomic Sciences in the College of Medical and Dental Sciences, Queen Elizabeth Hospital, all of which are hosted in the University of Birmingham. He is trained in applied mathematics and has been working in data science applied to the life sciences for more than 20 years, focusing on population diversity, precision medicine, cancer genomics, and systems biology. He has been applying as well as been developing cutting-edge methods to impact on a broad range of applications and health conditions, currently focusing on explainable AI approaches. Subsequently, he has been increasingly involved in leadership roles to conceive, establish, and lead new local and international initiatives in data science for life sciences in both industry and academia. Now to give us a lecture on explainable AI to leverage big biomedical data, application to the UK coronavirus cancer monitoring project, kindly give a warm virtual welcome to Professor Jean-Baptiste Cazier. Professor Cazier, the floor is now yours.
Thank you very much for this very, very kind introduction. And thank you very much for the invitation to participate to your new Bioinformatics series. A privilege to be here today and to have a chance to talk to you about our work in the UK. I'm going to try to share my screen. Hopefully it will be possible. Let's see. Yeah. There you go. Do you see the right screen, the proper screen?
Yes, JB.
Thank you very much. So here I am with a very, very long title for my presentation today. I don't need to describe all what I do. It's already been very kindly mentioned. So I'm very delighted to talk to you about what we are going to do, which is we're working on bioinformatics in a broad sense of the term. And today I will talk about one specific way we use the new method of AI, especially explainable AI, applied to biomedical data, in this case, the UK Coronavirus Cancer Monitoring Project, UKCCMP. So I would like to put this, first of all, in the context of what we do in general. What we try to do in general is to use a lot of buzzwords, which are, I hope you can see my my pointer here. It is that if you have a clinician with a patient, we can look at the patient from very different organs. We can look at it from many different omics. We can look at a lot of clinical information, a lot of anatomical information. We try to have all this information about the patient, compare it to the similar information from all the other patients, so-called big data. We try to integrate all this and come back to the patient in it. This is a big, big picture of what we all try to do. So today I'm only going to try to talk about a subset of this, which is effectively this part. Are we going to link the big data, the clinical data, and the environmental data together for the benefit of the patient? So what is this UKCCMP, the UK Coronavirus Cancer Monitoring Project? It started, as sadly everybody knows, about when the pandemic started to reach the UK about a year and a half ago. I work a lot with people working in cancer, clinician in cancer and oncologists. And there was a big question about how much does the COVID affect cancer patients? There were some rumors about that if you do have cancer and you are under cancer treatment, having COVID will be absolutely terrible for you. And the recommendation was then that you should stop your cancer treatment in order to avoid being killed by COVID. This is very alarming for all cancer clinicians because it means that the patients are likely to die from cancer, if not of COVID. So we looked at why people were saying this, and we identified this is information gathered by Shin, my colleague, and we tried to gather where this information came from. And we looked at, there were several publications at the time, very early on. So this is, as I say, in March 2020, go back in time. We knew very little about COVID at the time. And what we realized is that the studies this was based on were actually having extremely small numbers. So those were scientific studies published, but if you look, you have only 6 patients, 36 patients with cancer. It is very, very small number. And the conclusion then was, stop your cancer treatment to avoid to die from COVID. So we thought this is for coming from different places, and as well, it is very, very not powered. So we decided in the UK to set up the UKCCMP project. To answer that question, definitely, especially in the context of the UK population, does it affect the UK the same way as others? So over a weekend, as we decided to do that, we created this, which is, you can find the detail of the setup that we published in Lancet Oncology. Well, it was very fast at the time. Within 2 months, it was published. The idea is this is a map of the UK, And every green little dot corresponds to a hospital with cancer patients. And the yellow one are the people that were getting approval at the time. Now everybody got approval. What we had every single clinician, every hospital, most of the clinicians across the UK, sending us data from their own cancer patient every time they were getting COVID. So what we try to do is to gather all this information in near real time with human in the loop, meaning that we are checking that everything we say is correct. And then we send back the information to all the oncologists, the clinicians, to inform them about the results and whether yes or no they should stop their cancer treatment. I love to draw little diagrams that you may have realized, and you recognize the doctors here. Those are all the doctors at the center of everything. They collect information from their patients. They send this into a safe haven with the information about the patient that we decided to collect using red cap, completely protected for the health. This centralized system is then transported anonymized into a compute system that we have created in the Center for Computational Biology in Birmingham called CASLS, Compute and Storage for Life Sciences, where we could process and analyze all the data with some automatic report generation that we publish for the general public because the patient needs to know, but as well we send directly email to the patient. It was really almost a live system, near real time. All what we are doing, we are curating that our analysis were correct, and we are ameliorating our analysis all the time. So we set that up only in a couple of days because we had all the infrastructure, and at the same time, because unfortunately the pandemic was very strong in the UK at the time, we managed to get our first results in May. Within 2 months, we managed to get the answer because we already had 800 patients. 800 patients is more than all the existing study had been put together. And spoiler alert, but good news, very important news, we found no evidence that chemotherapy significantly increased the risk of mortality following COVID-19 infection. So this is a collection that we had at the time. In the UK, there was mostly the cases around London at the beginning, the first few months, but then it spread out. So this is, after this in May, we had 800 patients. There's a massive rise in number of cases. And what we did find, we looked, this is a forest plot, looking at the odds ratio for death if you do any of the treatment. So you can quickly see that this radiotherapy, you are protected. Immunotherapy, you look like protected. Target therapy and hormone therapy, all those look protective. But be careful, the confidence interval is still overlapping 0. So we do not say it's protecting, but we say at least it is not significantly at risk. So it is all good news for this treatment. Chemotherapy, on the other hand, is still high, it's above 1. So you could say it is at risk. However, when we say clearly, it is not significantly. We only have 800 patients, which is more than anybody else. We see it's a bit increased, but not very much. So you need to think about that. And we've been able to look into details about the severity of COVID and so on. So it was published in the Lancet very fast again, within a couple of months. So people could start to change their behavior and change their treatment. We still managed to gather some information from the clinicians. So it's a bit of epidemiology, where we could identify that age, gender, and comorbidities were associated with high mortality in cancer patients. It's pretty much the same that we were finding actually in the normal population. Everybody knows now that older people and essentially are male, and especially if you have cardiovascular disease, were at risk, increased risk at the time. So there was no difference between the cancer patients and the general population. And you can see here the statistics that we have. Being a male, being older age, cardiovascular, or hypertension were very in the list. But this is just after 2 months. So we continue collecting data as we are continuing the analysis. And a couple of months later, we managed to gather 1,500 patients. So you can see a few more months. We managed to get more patients, which allow us to do further analysis. And they we published in Lancet Oncology very quickly. So in this study, we first confirmed that age and sex are the very important parameters, but we could be able to look inside each of the category at the different cancer subtypes. And hopefully you can see. So here we have all the patients. You have the men and the women separately, and the color code indicates how severe it is. The more close to the red, orange is bad, and the greener the better. They are ranked by severity, and you will spot that at the bottom you have breast cancer and femoral genital organs, such as ovarian cancer, which are mostly green. It just reflects the fact that young women are usually having those cancer, and they are not the one which are affected in general. At the top, we spot that leukemia, myeloma, prostate, and lung cancer are all very, very important. So the blood cancer, prostate cancer seems to be the most important cancer relating to COVID, which means that not only we have to think about the treatment, but we have to think about the cancer type to make a conclusion. But something I like to show to our students actually is that although when we do an analysis univariate, which means we just look at the number of patients, we can see that prostate cancer patients are very, very high. However, if you do multivariate analysis, which means we correct for age and sex, the odds ratio, instead of being from 2 with a very significant p-value, the odds ratio becomes 1 and definitely not significant p-value. So if we're only doing the analysis based on this, we'll say prostate cancer patients have a problem. But in reality, if you correct, it's gone. Why? Simply because prostate cancer is only for men. Essentially, it is for the old men. This is exactly a confounder of the problem. So it's not prostate cancer that makes you at risk. It's the fact that old men have got prostate cancer. Inversely, as I mentioned, breast cancer and ovarian cancer was very significantly protective, very significantly protective. But again, if you correct for gender and age, it's not protective anymore. It's just these people happen to be young women, and therefore they're not at risk. Still, and very importantly, leukemia showed you at the top of the list was blood cancers. It was very high risk, a risk of 2, quite significant, but not that significant. When we correct for age and gender, actually the risk was higher and the significance increased. So leukemia is really something that needs to be looked into. So we continue gathering information. This is in a revision mode now. It's unpublished data. So after a few more months, luckily the number of deaths from COVID stopped or reduced dramatically. And we managed to have around 3,500 patients. So we could do further analysis. This is a mirror image of the previous one. You will recognize the color, but because we have bigger sample size, we can show the numbers behind it. The trend is the same. You can see all patient male women here on the side. The younger ones are green, so not high risk. The older ones have got higher level, more on the men than the women. And if you look at the disease actually now, we can see that we have all types of disease linked to the blood, plus the lung, which is unsurprised, or which is an important finding. And the rest is actually linked to gender and or age. So this is a clarification of what we found. And now we are able to do further analysis and looking into the significance of those pictures, bigger numbers. And if you look at this picture, which is the same order of this, it's sorted by importance. And you can see that the very, very broad diversity of the risk to die from COVID, depending on your cancer type. Of course, the arrow bars are still big, but the trend is very, very, very clear. Most of those are not at risk. The only one which are prostate, but as we said, if you correct, it's going away. Myeloma, CLL, CML, and leading to male cancer, which is a correction. So you can see the very, very big difference with what we can do. And we can go back to the original question about whether the cancer types are actually, the treatment is actually dangerous. And you remember that all of those were quite low, but with very broad confidence interval. Confidence interval much smaller now. You can see target therapies, bang on, radiotherapies. Most importantly, chemotherapy, which was all over here, with the confidence interval has moved from here to here. So now we can confidently say that they are all not at risk. All the treatment are absolutely fine. This main thing you need to think about is your kind of cancer. So this is what we did, the classic analysis using the power of classic computing and analysis using normal statistics. But the title is about AI. So we do work a lot about AI. And we're thinking, okay, we now have a lot of data. Let's see what we can do with it if we can do something more, because there have been a lot of promises of data science and AI. You may have seen, you can do image analysis. The computer will do very fast. If you do clinical judgment, some say it can do better than the clinician. It can help as well the hospital to run the workflow to deal with the patient, which is very important in times of COVID because of backlog and so on. It can help with surgery. It can help even to do a consultation with nurses at a remote distance. So AI can solve everything, all right? And there's a lot of buzzwords, again, that are floating around, and I want to explain a bit a few of them. So big data, this is quite simple. Big data is a lot of data, and it allows us to do further analysis, but that's not really new. Data mining is just trying to get the information out of this. Machine learning is a specific technique which allows us to extract information and make a prediction from the data. And artificial intelligence is another level of it, which allow us to do machine learning, but other things such as identifying pattern automatically. Explainable AI is more recent, and it is one step further from AI, which is often called a black box. We can predict something, we just don't know why. Explainable AI is actually trying to transform the black box into a gray box, or a bit more transparent box. Try to understand the underlying mechanism. You have as well deep learning, which is the exact opposite, which is just a big computer doing a lot of things, which works, we just don't know why. So this is all those different directions of what we want to do depends on the complexity, the amount of data we have, how complex they are, and the kind of model we want to do. And you have all the other buzzwords you can see here. So the method here that we have been using, we're focusing on explainable AI. And the whole idea is we want to learn from learning machines. If you do classic AI, all you want to do, prediction for prediction sake, automatically driving a car. Don't care how it works, as long as it works. In biology or in a clinical setting, what we want is to understand why is it working. We want to understand the structure in the predictors. So the method that we are using is this explainable AI. This is about. We're using iterative random forest, which is an advanced version of random forest. There have been the idea is that this is a typical machine learning technique. You have a lot of data. You make a function of the data. You want to predict the outcome. Instead of just looking at this in a pure algebraic way or statistical way, we try to understand this data, create a network behind it, see, understand the mechanism behind. Same here, simplify this, and then we try to associate directly what this works. So this is a method developed by from our colleague Ben Brown, who is now in Berkeley, and it's been published in PNAS and BASU about the IRF method. It allows you not only to predict, but these are actually the different features that you have, and it allows you to see the interaction between the features. This is why we're trying to use, in our case. We're going to use explainable AI on UKCCMP. So this is work from Joel Mitchell with my postdoc from the Alan Turing Institute. What do we have? UKCCMP, I explained to you, is a big structured data. We have all the observation, which are all the patients, more than 3,000 patients. We have all the features, all the clinical feature, all the age of the patient, the severity of the disease, all what I showed you earlier. So it's very clear. And the outcome we're trying to predict, the label, in this case is very clear. We know that in our patient, unfortunately, 30% of the people reported died with COVID. So the outcome is, did they die or not? So we have a very clear structure, obvious transformation to use explainable AI. The key thing in this picture is actually those arrows below. What we do with explainable AI and IRF, we're able to figure out which features here. So for example, is age linked to severity? And how they work together to predict. It's not a black box at all. We're able to understand what's inside the box. This is the key part. So in order to do that, we're defining several models. The first model is use all the features. We have 102 of them. And we try to use all of them to predict what's going to happen, but it is too late. So we just want to understand what are the key factors. We expand our model. I will go in detail further on to see if we can get more information from it. But the last bit of what we try to do is some of the features we gather are actually linked to COVID. So when people have COVID already. So we try to remove all the information related to COVID and see if we can predict beforehand who is going to be at risk. So we look only at age, comorbidities, but not severity. So how is our model performing? We use RF. Hopefully you're familiar with this kind of curve. So it's a ROC curve. The whole idea is this is the picture of how well we do, and the surface underneath shows how well we do. The closer to 1 would be perfect, 0 would be terrible, and 0.5, which means we just predict randomly, which is not that good. So you can see that our model, with all the data we have, is a very good predictor of survival. We have 92% covered here compared to the middle line of 0.5. In AI, what we want to do as well is how well we predict how correctly we do predict the precision of our call. So it's a different curve. The figure is slightly different, but again, the idea is we need to look at this number. The area under the curve is very high, 0.7. In this case, we don't compare to 0.5. What we compare to is a proportion of people in one class compared to the other. So I'll say we have about 30% of the people who die. So we have to compare 87 to 30%. So we are doing very, very well in our prediction with our model. But the key part in what we want to do is this. We want to understand the interaction. So here's a table of the most important interaction between the features. And here are pairs of features that go together. Sometimes we do have 3 features and we can see the impact. So this is like p-values and effects. I'm not going to detail. What I want to highlight is I put a bit of color here because you can see that the same feature come again and again and again. Age is at the top of the list. And it comes again in pair with different things. Age, 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 you can see. The other feature that comes often in red here is severity. When the patient admitted to hospital, we have a measure of the severity. And it's not a surprise, the severity is a very good predictor of death. So those two together and severity is happening very, very, very often. The third one, you can see is actually 2 of them, third and fourth, is longitude and latitude. I put both of them in green. This seems to be quite important parameters coming recurrently all across. So what we try to do is understand which of those features are important. So this is a plot of the stability, which is the significance of the pairs we have. These are the same name, you can't read them, but the same name of my first column. And we put a threshold. If your stability is higher than 0.75, you can see you have a big drop after this. We can look at the number. When you do our full model, we recover 66 interactions. So 66 pairs of triplets. But because they are pairs of triplets, in reality, we only have 18 features coming back again. This just combination of those 18 makes those 66. I want to have the most significant one. You can see a drop here. So if I do a significant one, you only have 32 here, only 32. And these 32 are covered by 7 features. So although it looks like we have a lot, there are only 7 features explaining most of it. Those features are severity, age, latitude, longitude, IC63, which is the ICD-10 code for male cancer, prostate cancer, and similar. ITU, that is whether the patient has got to go to intensive care and whether they need ventilation. So the first one is exactly what we could spot by eye, but you can see here by counting which one are coming the most often, this is what we see. Severity, very clearly something which is something you measure afterwards, and those ones which are independent actually of the disease. Whether you have COVID or not, you will always have this information, but not the other one. Importantly, there's no direct gender effect. Look at this. You don't see, oopsie, you don't see sex anywhere here or gender. It is not apparent in the top 7, which is very weird. It appears probably in part here because those are the male cancers, only male cancers. So it may be here, but it doesn't appear significantly. So another way to figure out which features are the most important is to use a so-called Gini score. So because we use iterative random forest, Gini score tells you how much a feature is helping to break down the random forest trees. And we have a score for those. And this is the score, you can see here, I listed them. The list is very similar to the previous one, but we have a score. It's slightly different. At the top, you have severity, much, much higher than everything else. Then you have the age, and then whether you need to have oxygen, so that is the ventilation, latitude, longitude, and so on, that come. So this picture is far more accurate than the previous one, because this is a pure computational and quantifiable thing. So from this, we can see that we may want to consider alternative models. First of all, we may want to drop the top one, because this is so big. This may be the tree hiding the forest. If you remove it, we may discover something new. And we may want to continue and drop all the other one below and see the importance of it. The other things we may want to do is, when the patient have got COVID, it's already too late to act, or it's more difficult to act. So what we're thinking is, can we predict from all the information which is not related to COVID, who is going to be more at risk? Who should we look more carefully? Who should isolate more than others? So we create a model when we drop severity, we drop anything linked to the treatment or shortness of breath, okay? So we keep only something like age, sex, comorbidity, where they live, and so on. And this is actually dropping about 40 features. So we only have 60 features left. Interestingly, in this picture, sex, to come back to what I said, so the gender effect is very low. It's here, but it's 15th down the line. So it's not very, very strong effect, but it is present. So how is our model doing when we drop features? So the full model, to remind you, is high up here, so it's very vague. If you drop the top feature, which is severity, you can see the model is not as good at all. There's a massive drop. And then it continues to drop slowly the more feature we drop, which is normal. We drop information, we lose. But it's very interesting to see severity explains so much, but everything else doesn't drop too much in both cases. You can see the numbers here. And very interestingly, if you look at the so-called a priori model, which is the one when we don't have anything linked to COVID, with only external 60 features, is here. So it's the worst, of course, it's the least information, but it's not that bad compared to the rest. It's still quite a good predictors. So we already predict, yes, 70%, which is much better than 50%, and the 49% compared to the 30%. So we do still quite well. So with this model, we're able to predict which patients with cancer are likely to be at risk of COVID, who should take more care. That's the line you should compare to. So it's doing still pretty well. So one thing is, the first thing is when you drop a feature, the same picture as before, you can see here, you can select. So if we have the top one here, you remember all the interaction with our full model, we have 32 interaction and 7 features behind it. If you drop the top one, severity, this is a new picture. So all the severity one will have disappeared, and we can actually recover 95 interaction with 25 features. So we can gather more information by removing the most obvious one. And if you look at the a priori model, which is non-COVID related information, we can identify 126 features, which is a lot, which is per interaction, which correspond to 41 features. So by improving our model, we can, if you miss some information, we can identify still more knowledge about what is happening. The other thing we can do with our a priori model, at the moment, we use a very clear definition of who is dying, who is not dying. Because it's prior to COVID, we may want to think as well how severe COVID is. So if you have the a priori death, you remember that's the number I showed you earlier, we do quite 69 and 49. If we change the outcome, the phenotype from death to being critical with COVID, we have 21% in this category. We still predict just as well, but the precision is not as good. This is for critical. And if you look for people critical or severe, which is even less, we are able to predict very well who of the cancer patients are actually going to have a severe reaction. So we can narrow down, and all using all these technologies and techniques, we can narrow down all what we do and be more useful for the patient. Remember, it's a close work between the clinicians and the data scientists. There's very little biology here. So if you look at this model, at the top of the list, if you have good eyes, but I put it in bigger letters, you have age, longitude, and latitude in the a priori model. So this is what matters more than sex. It's age, longitude, latitude. Where how old you are, can't do much about it, but where you live, which is very weird. Because then how does longitude and latitude matter? this is actually a subject of my research, which is population diversity. What do we have? This is a map of the UK and the genetic diversity of the UK. This part of the UK, which is all around London, is actually linked to the Dutch people. They look very similar. There's the Anglo-Saxon, the part. The northern part looks like Norwegian. This part looks like the French, and so on and so forth. So is longitude, latitude corresponding to the underlying genetics? Maybe. Does it correspond to access to care? Because in the UK, you don't have the same access all across the UK. It depends on your geography. This is mental health, for example. You can see the diversity. We call it postcode lottery. Or is it socioeconomics? The South, much richer, and the North, less poor. Is the longitude, latitude is going to predict who is going to be at risk? It could be many, many things. So it's quite difficult to do this. And this is actually part of the reason why I've got Alan Turing postdoc working on this, because this is what we are trying to do, try to compare population across the world and try to figure out which information is relevant, because you do not always collect all of it. So we learned a lot of lessons from this. First of all, to be able to react so quickly to tackle the UKCCP within a couple of days and gather information within months, and it's because we are ready with the environment. Not only the infrastructure, we have these castles that are created, but we have all the expertise between the clinicians, the oncologists, and the data scientists. And maybe most importantly, we have this culture of working together. We really, in Birmingham, University of Birmingham, we like to work together. So this is something that's been making it happening so fast. So we could act quickly and decisively. So we could collect the data at the very beginning of the epidemic, and we had specific goal. Is chemotherapy or treatment bad for you? Very clear questions. What was challenging is, because we want to be fast and we had a clear question, we could not collect everything. Therefore, we cannot answer every question. Our data is very good, but it's limited. And therefore, we can't transpose what we found to another country so easily. We realize as well the data is very diverse, and the data needs to be protected. So it's very difficult, especially if you want to compare between population, between countries, very important, but the data often cannot transmit. So we need to find a way to do this. And so we need, every time we create new approaches to analyze the data in different ways. So for the future, because this will happen again, we need, when we do set up this kind of environment, we need to create, allow for the diversity of the data. We should not have ontologies which are too strict. The ontologies need to take that into account, especially if we compare worldwide. What's important in the Philippines is not the same that is in England. The disease, the way you measure things, and so on and so forth. Data protection, absolutely critical. You need to protect the patient's information, so we cannot transfer data. And as well, we need to know that we are asking the same question, especially worldwide. Something means have slightly different meaning. But it's possible. We are creating novel method, novel federated approach for the data. We just make sure people are linked up and coordinated. And we need to link, again, this is a culture here. Scientists need to work with clinicians, with infrastructure, with the local community, and policymakers. Everybody needs to work together. And we just had happened to publish just before, it was published in the pandemic, but we had worked before on a paper saying that if you want to take care of all this data and the diversity, we need to work all together. And this is why we are ready, because we are already thinking about it. Just as a last conclusion bit is that XAI, explainable AI, can be used beyond UKCCMP. It was very well because it was pretty structured data, but we have other data linked to COVID. So we have COVID surge, for example, which is a collection of all surgery and the impact of COVID surgery from worldwide. So we have that information, and we're starting the project to analyze it with this method. Completely different thing is we have fitness gene. In this case, the outcome is lifestyle and fitness. How important is your gene background, genetic background, to understand compared to your environment and the kind of sport you do? What is the best exercise for you, given your gene, to have a healthy life? And we have data from all over the world as well for this, so a lot of challenges. Completely different scale. We use a very same method in porous air, but it's a CUK program. We have different types of omics data, similar to what you are generating in the Philippines. Genomics profile, proteomics profile, all site of profile, all of those, and we on specific patients, and we try to integrate it to understand what is happening there. And we can include that as well, just for the clinical setup, and so on and so forth. So in conclusion, AI can make a very, very good use of a diversity of clinical data to predict the outcome. But it's just a predictor. In terms of biology, it's frustrating because it doesn't give you all the answers. So XAI is actually moving forward and giving you an idea of what is the mechanism behind, but giving you what is interacting, what are the features working together. It's still hard to interpret, like longitude, latitude, how do they link to each other? It's quite difficult to know. But we need to have a very good predictor if you want to retrieve the interaction. We need to know what is the question, clear questions. The other big problem we have is how do you validate your results? We have all the UK data, pretty much, no. But how do we validate? We don't have other cohorts. So we only can compare to other countries, but it's not exactly comparable because our N equal all. So maybe we can split our cohort or do functional studies and so on. This is a problem of AI, like all the time. So I want to conclude by thanking everybody who is behind the UK CCMP. Those are the senior people, 4 people who are the co-lead of the project, and here are all the data scientists who did all the work, and the many clinicians that have been supporting it, and as well as the support of the Alan Turing Institute. On this, I will thank you and be ready for your questions.
All right. Thank you very much, Professor Cazier, for that. Thank you very much, Professor Cazier, for that intensively detailed and insightful lecture. Truly, while we are all in the fourth industrial revolution that promulgated a data-driven society, the health sciences should be no stranger to artificial intelligence and machine learning, given how it has significantly sped up information processing and analysis towards developing insights and solutions through prevailing concerns of humanity, including, of course, as you have mentioned, cancer research and COVID-19 research. So we now enter the open forum stage of today's activities and spend a few minutes to address questions and comments that audience members may have for the good professor sent via Slido. So, okay. I got a pool. I pulled together the questions from Slido and also interjected mine as well. And there are 2 prevailing classes or categories of questions that I've seen here, right? So I hope this should be a little bit exciting. So first is regarding the studies that you have made, okay, particularly out on the published ones and even the unpublished ones. One question here is the data that was used to generate the insights open source, in case and somebody else would want to conduct benchmarking or alternative analysis on the data?
Well, this is a very important question, and I would love to say yes. However, we are not allowed to do that. So, and that's the point I made at the very end, that we need to be able to share information. However, at the same time, we need to protect the patients. So the data is not open source. However, we are very welcoming and we do have collaboration. So we have, if someone is interested, we're very, very keen to work with you to have access to data through us, and we can work together. For example, if you want to compare, and I would love to do that, we do that in some country, the Philippine COVID cancer patient, if you want to compare the outcome and what is important, I would be very happy to work hand in hand with you. We can tell you exactly the scripts, we can compare the outcome of the results and go further from that. But we cannot just give it away. You need to be joined and part of the project. And as a collaboration, we can work together, absolutely.
All right. So that said, just just give Professor Cazier a call, and he could actually work with you. Hopefully, right. So next question. Okay. In your studies, do you have any mortality rate of those illnesses before the pandemic? I think this means the cancer. Cancers. Were you able to match it with the odds ratio of death with your data on the COVID deaths?
Yes, so there are 2 ways to understand. I'm not sure whether those are linked to the comorbidities or to the cancer type indeed. So it is a very important point. And the fact is, in this case, when we compared the same population, who is dying, who is not dying, with the same cancer. So we do not compare to the generic population, we do compare to the cancer population. So this, if we talk about the death rate, the mortality rate because of cancer, it's already taken into account into the way we have designed our study. So it is not a problem. In terms of comorbidities, it's exactly what we are highlighting. is that the comorbidity are important in different ways. And correcting for it is not an obvious thing to do. It's a complex statistical problem.
Okay, thank you very much for that, Professor. Okay, here's another question regarding the studies. When does a disease start to be considered a comorbidity? How did you decide from when is age important to be taken into account?
I'm not sure I understand this question. So all we have is very clear clinical outcomes. So we register the patients. When do they come to the, so we have the information about all their cancer history because they're oncologists, they're cancer doctors who is entering the information. Then they just tell us when do they enter the hospital or when they tested positive. And then we know the outcome. This is all what we have. Then we measure, and that's the problem all over the world. We just say, were they under treatment 28 days prior to testing positive? It's not ideal, but there's a measure that everybody in the world is using. So some people may die of cancer with COVID, not of COVID, and we are very aware of that. There's a problem we have all over the world, especially we are looking at older people. But again, because we compare within our cohort, we have everybody, or almost everybody, we are able to link into this in detail. You should be able to correct for this.
Yes, if I understand correctly, right? At least for the concept of including age as being a significant factor in determining survivability, that was age was part of the data set of the fields in the data set. Did I understand?
Absolutely,
Did I
it's
understand?
one
Yes,
of the
yes, yes,
feature.
yes.
One of the feature we do collect, and this is
Yes.
what comes out of the study. Age is the
Yes.
most important. We don't decide it is. It's just
Exactly,
what
yeah.
pops out. Absolutely.
Exactly, it's part of the it's the machine learning, or it's the method that based on the data. It turns out that age is an important consideration in determining survivability.
Exactly,
Yeah,
and if you look at the first studies, to clarify, this is why I showed the slide when you do univariate analysis, that is, we don't correct for anything, a lot of concepts come up. But because we identify age being important and gender being important, we correct for them and some comorbidities, and then we're able to correct for this confounding effect, such as prostate cancer. Because we take into account age, things like prostate cancer disappear because the data tells us age is important, and we can refine our analysis this way.
Okay, thank you very much again, Professor. Okay, now the next question is about impact of the study of this, at least one of the studies that you did. So how has the UK CCMP transformed clinical management of cancer patients I suppose in the UK?
So we believe and we understand this changed the cancer management worldwide, because this is why we made an effort to publish in the Lancet, which is read worldwide and so forth. And that's why as well to be happy with to just mention that the journals have made a big effort to publish rapidly everything on COVID to share information. So we have made a questionnaires about oncologists in the UK and asked them whether our study have changed their practice, and everybody said yes. Everybody has said they have restarted the chemotherapy and all the treatment for the relevant people. And anecdotally, we know it's a case worldwide. People have restarted everything. But it is very, very important because we are driven by looking after the patient's well-being, and this is why we spend a lot of effort. So we believe it's not the first part is not the most difficult work I've ever done in my life, but it's probably the most impactful because it affected the life of so many, just by doing a good design.
Yeah, and that's good to hear, because that's what science is all about, right? Making impact on society and humanity at large. Yeah, that's good. Okay. This question is also regarding the study. This is actually from me. So, what were the most unexpected results that you got from your research on COVID mortality in cancer patients? Was there something that jumped out that whoa, I did not expect this, or?
Well, two things which I try to highlight as well. So one is that sex was, when we do pure machine learning approach, sex is not so high in the list while it is in the classic epidemiology. But that's because it comes from analysis, number one. But number two, longitude, latitude comes so high. Where you come from matters. And as I say, it's very well known in the UK. We have a postcode lottery that there can be problem. It could be as well because of the cluster of different ethnicity, People have different access to care. We do not know exactly. We are still working on trying to identify where is this latitude, because it's not really where you come from that matters. I doubt it's about the amount of sunshine you get, but it is something else. It is it's just a marker for something else, and we are struggling to figure out what. It is complicated, but it comes so high. That was a big surprise. It's so high in the features. Where you come from matters. It's too late to move it. Or actually, I don't know. We don't even know if you move. Does it matter, or is it about where you've been living the last few years?
Yeah. Well, I guess that's another research problem or research topic that you could look into. Definitely.
Absolutely.
Okay. Yeah. Okay. Cool. All right. So I guess that's for the the questions regarding the study. So now I'll zero in a little bit, or at least I'll focus in a little bit on the explainable AI, or at least the machine learning aspects of the talk. Right. So here are the questions. So first, thank you very much, Dr. Cazier, for your insightful presentation. Okay, can you discuss further how explainable AI help us provide a quote-unquote gray box solution to real-world problems?
Yes, I decided not to make any plot of what random forest is because I would never have the time. And already, I think I put a lot of information in my presentation. But the whole idea is, if you have this big matrix, as I showed, with all the patients on one side and all the features on the other side, the black box is we just have a function that transforms that into the outcome, dot, whatever happens. In this case, the key part is, I say, the little arrows below. It is in the RF model by creating, because we create we create forests, we can see which of the features are coming together in our trees. That's technically what's happening. We can see the features coming together and which one by going together and with a direction, whether they go high or low. We can highlight which pairs are pairs or trios or fours or 4 or 5 orders, which pairs are contributing to the signal. It's a bit like in PCA, the eigenvalues, except it's far more complicated, but it's conceptually the same idea. Instead of having one, and this is a key part because it's why we do a mechanistic. We can see that something is interacting with something else. So we use the method on enhances, for example, and we're able to link enhances to motifs or transcription factors as the actual movement of things, which is give more insight than just a prediction. Then here's more work, it's more question. Of course, it's a gray box. I didn't say it was fully transparent yet.
Yeah. Well, thank you very much for that clarification on explainable AI being a gray box solution, right? Okay, here's another question. So you mentioned, among others, a priori and random forest. So a priori being an association rule based method. As among the methods, machine learning methods used in the study, did you also try other machine learning methods, or at the very least wrapper methods for feature selection?
No, we haven't done that because we have a limited amount of manpower, unfortunately, and we did focus essentially on the RF because we believe it is this gray box approach, and it's already that takes a lot of time and understanding. So we haven't tried anything else. But yes, we should when we have time. We will. I'm sorry to say that.
No. Okay, maybe just a follow-up question to that. Because you've used random forest, right, as a template.
Iterative random forest.
Iterative random. Yes. Is this is other classic machine learning methods also possibly applicable to explainable AI researches? Have you done that? Have you ever thought of? Yeah.
So there are two parts. So most of the techniques around are just AI or machine learning. There's a big push for the last couple of years now about explainable AI because we want to go beyond. So IRF is just one of many methods. There are other methods we could try. We just decided to use this one because the person who created it, or one of those, Ben Brown, was my colleague for a while. He was next door, and we thought together we should use it on many things. That's why we started with this one. But there are other methods, and the name just escaped me right now. But it's easy. There are quite a few papers published. Actually, we are writing with Ben a paper on this. So I could not published yet. But we'll have all the references. There are many methods you can find online. But it's not the classic machine learning. It's not random forest. It's not explainable AI.
Yeah.
Regression is not random AI, and so on and so forth. It's only it's a new category.
Yeah. Okay. Thank you very much for that talk. I guess actually this question just popped in, and this is actually related to both the studies and also I suppose the AI that at least the analysis done using explainable AI. Out of curiosity, how long did it take your team to come up with the results? So how long is the generation?
It's how long is a piece of string? We are still looking at the results. Okay. This is research. We try to better understand. So as you see from the UKCCMP, the first part, we did the very classic one very fast, which was essentially spending a lot of time making sure the data was correct, well organized, and then we do classical regression. And so that was quite fast. But when we do a new method like RRF, which is new and never been applied to this, we need to spend more time to understand properly what it means, create new sub-methods. So we're developing the method as we go. So it's a never-ending story. To run it, it takes only a couple of days, but if you're familiar with AI, the key part is not the running of the AI. The key part is the feature engineering, which is deciding how you represent your feature, how you collect them, how you narrow them down. And that can take months or if not years. But you can do one thing and it's ongoing. So the result we have, we think we are good enough now. We've been working on this for a year, but we had good results in 1 month, but I'm never satisfied. But I like to have more because the data change. We understand the data is back and forth. So the answer to the question is, yeah, how long is a piece of string? I'm sorry, it takes time.
Okay, that's that's fair. That's a fair answer. But two things I gathered from there, right? One is, you keep pushing, you never get satisfied, and that's a healthy, it's science, right? You keep pushing the boundaries, okay, of how far you could get to learn things so that you could improve your current solutions or current state of the art, right? And secondly, even explainable AI and clinical studies such as this, where AI is applied, is not spared from the usual data mining timeline, where you spend 60 to 70% data gathering, data processing, and then the analysis is just a small portion, and then followed by a couple of more a couple of longer periods for introspection or analyzing the data. So yeah.
Yeah. On this, if I want to add something, is that when we do pure research, time doesn't really matter and the outcome doesn't matter. We just try to figure out something and expand the knowledge. Here we're dealing with patients, so we need to be extremely certain what we say. So we are extremely careful about what we say, so it takes time. But at the same time, because it's COVID and we wanted to have this near real-time information, we had at the same time to go very fast. So we have very clear, narrow answers that we are very certain about. So this took us a couple of months only. But when you try to push the boundaries, yes, it takes longer time. So this is balance between, because we want to have an impact on patients, that's our number one priority, is how do we go fast enough for the patient, but then we keep on pushing at the same time. So it's a difficult balance in the world of clinical application of research.
Oh, definitely. Okay, so thank you very much for that. So we're down to our last question. Okay, if one were to set up computing infrastructure to conduct explainable AI analysis, such as one you did, what would be the recommended computing specifications or requirements? Is it just the same as having a high performance computing facility, or do special computing apparatuses are special computing apparatuses, like for example a GPU, for example, or
yes. So there are many ways to answer this question. So I mentioned castles at the beginning, the infrastructure. One way we worked is we decided in where we are that we need a lot of compute in general and a lot of data storage, and transferring data to the cloud far away costs a lot of time and money. And talking about sequencing data and so on in general, or imaging, it takes 4 ages to upload them and then to do the analysis. So what we designed for us is a local cloud. It's called Bear Cloud. It's our local cloud. So we have a lot of CPUs and GPU locally for type of data. That's the overall model, but it doesn't satisfy everything. We work with the CERN, and the CERN has got their own computing. So there's the physics department. So we do work differently. So for different questions as well, it will be different. So in our case, this study, the amount of data is not that big and complex. So we could easily put it somewhere up and compute it. But it's not too expensive because our data set. Some of the other applications I showed you at the very end are much bigger, and they will need a dedicated setup. So we actually bought the biggest GPU in the UK at the time of we buying. It was 3 years ago now. It's not anymore, of course, but it was at the time from Lenovo. But what I want to say as well, IRF, I believe, still holds the record for that's the method that was used for I forgot the name of the prize, for the biggest computing ever done, which has been done in Argonne in the US, Oak Ridge Laboratory, by Ben Brown and Dan Jacobson. They hold the prize for using this method, IRF, for the most expensive or the most flops, I forgot, exaflops that they have. So you can go very big for the same method, just different data type. And they use it on poplars, if I remember. So the trees, the genomics of the trees.
Okay.
Thank you very much. The question again, it depends on what, but you can do it cheap if you don't have too big data. It depends on your data size.
It's still the data size. Okay. So thank you very much for the advice, Doctor. And we've run out of time for an forum. I guess there were other questions actually that suddenly popped up, but unfortunately we have to stop now. Okay. So thank you very much, Professor Cazier, for graciously answering the questions and for providing additional insights and input on the topic. Okay, so now we enter the latter stage of today's activities. I now hand back the floor to Dr. Tolentino. Dr. Tolentino?
Yes, thank you for that engaging question and answer portion, Professor JB and Dr. Yap, and also to our participants for submitting your questions. Now, for the other questions that were not read in this session, you may contact PGC Mindanao through our email address, which we will flash later so that we can relay your question to Professor JB. At this point, we would like to give our appreciation to our speaker and moderator. But before that, I would like to request our speaker, Professor JB, and Dr. Yap, our moderator, to turn on your cameras again. I think they're already turned on. And we would also like to request for our program director, Dr. Lair Murao, to turn on your camera as well. Dr. Lair?
I'm here.
Oh, okay. Now let me read the citation. First, this certificate of appreciation is proudly presented to JEAN-BAPTISTE CAZIER for being the resource speaker on Explainable AI to leverage big biomedical data, application to the UK Coronavirus Cancer Monitoring Project during the second lecture of the Bioinformatics Lecture Series held on October 29, 2021. Signed, Dr. Lair Ani E. Murao, Program Director of PGC Mindanao. Thank you, Professor JB. Our next certificate, this certificate is proudly presented to Dr. John Michael Yap for being the moderator during the open forum of the talk, Explainable AI to Leverage Big Biomedical Data, application to the UK Coronavirus Cancer Monitoring Project by Professor J.B. Cazier in the Bioinformatics Lecture Series held on October 29, 2021. Signed, Dr. Lair Murao, Program Director of PGC Mindanao. Thank you, Dr. Yap. At this point, I would like to request to keep your cameras open, Professor JB and Professor Yap and Dr. Lyer, for a photo opportunity. So please tidy yourself up and show us your best smile. One of our staff will give us a cue for the picture taking.
Okay, 1, 2, 3. Thank you.
Thank you, Paul. We also would like to request for the rest of the organizers of this event to turn on your cameras for a photo op. I'd like to call on the rest of the Bioinfo division and the R&D division staff to open your cameras for the photo op. Again, our staff will give us a cue for picture taking.
All right, 1, 2, 3. Yeah, thank you.
Okay na? Okay. Thank you, everyone. Thank you for that. Wala bang clap dyan? Now we'd like to hear from our participants on how we did in today's activity. On the chat box, our staff will be providing you with a link for the evaluation form. Please fill them out before the end of the day. All respondents will receive their certificate of attendance once the survey is submitted. So I think the link is already in the chat box. Okay, thank you. Now, for future events and to know about the services that we offer, please visit the PGC Mindanao website or our various social media accounts. So as you can see in the screen. You may also contact us through the number shown there, 082-293-0302, or email us through pgc.upmin@up.edu.ph. Our activity today is just the second offering of the exciting lecture series on bioinformatics. On November 2, so that's next week, we will be having Professor Janos Christon-Vizi to talk about the 3D high-content screening for identification of autophagy modulator small molecules using hypoxia. We hope that you could join us again on November 2. Again, on behalf of the R&D and the Bioinformatics divisions, I'd like to thank you for attending the second lecture on the Bioinformatics Lecture Series of PGC Mindanao. We hope that you have a nice evening ahead of you, or maybe day, depending on where you are. And stay safe, everybody. Bye. And thank you.